Alright, so you are ready to take notes on simplifying radicals. Some of this may be a review, but some of it may not, so please get ready and make sure you are writing as detailed notes as possible. Alright, so anytime we are multiplying two radicals that are the same index, so both of these are square roots, whenever we multiply them, we multiply the radicand, or the number underneath the radical, okay? So square root of a times square root of b equals the square root of ab, where we're multiplying a and b underneath the radical. So you can see how this works, because let's look at the square root of 36. Well, the square root of 36 is 6, right? Well, look at square root of 4 times square root of 9. Well, remember, square root of 4 is 2. The square root of 9 is 3, which still gives me 6. But look, square root of 4 times square root of 9. If I combine those, I get square root of 4 times 9 underneath the same radical, which is the square root of 36. And again, we end up back at 6. So this rule will always work. Alright, so let's try square root of 2 times square root of 8. If I combine these together to be square root of 2 times 8 all under the same radical, I get the square root of 16, which now can be simplified as 4, right? Because the square root of 16 is 4. Now let's take a look at square root of 3 times square root of 48. Well, the square root of 3 times 48 all underneath the same radical. 3 times 48 gives me 144. Square root of 144 is 12. Okay, square root of 3b times square root of 2a, both are square roots, so I can write them underneath the same radical, 3b times 2a, which 3 times, I'm going to combine like terms here, 3 times 2 gives me 6, and then I just get ab. Now this cannot be simplified anymore, but we did put it into one radical, so I can't do anything else with that guy. Alright, so there are a few ways to simplify square roots, and one way is to create a factor tree. Now, factor trees are whenever we break a number down into all its prime factors. So let's look at the number 75. 75 is 3 times 25, and 25 is 5 times 5. So, in another way of saying this, 75 is 3 times 5 times 5. Now, 5 and 5 are doubled. So anytime I see a number doubled up, that's going to hop out of the radicals. So if I do 3 times 5 times 5, any number that is doubled up, that means I have 3 times 5 squared, right? Because 5 times 5 is 5 squared. So this guy right here, this 5 is going to hop out of the radical. So this guy hops out and comes out front. So I get 5 times the square root of 3. Now we normally don't have to write this little times in between. We just have it be known that it's multiplication, so you don't have to write that. Now another way of doing this is to look for perfect squares inside of a number. So this is the most common way of doing it. So the square root of 75 is the same as 3 times 25, right? Well, 25 is a perfect square, and because of my product rule, I can write this as the square root of 3 times the square root of 25. Where the square root of 25 is 5, right? So again, I get 5 times the square root of 3. Again, you don't have to do the dot in between because it's known that that's multiplication. So these are two different ways of looking at it. When you have really big numbers, this might be the best way to do it, is break it down in your factor tree. But when it's something that you can kind of spot and see the perfect square inside, maybe this is the one way you want to do it. Or you can combine the two methods, whichever is easiest for you. Alright, so this is just a recap of the things I just said. So the step 1 is going to be determining the largest perfect square factor of the radicand. Remember, radicand is the number underneath the little house, okay? So the radical is the house, and the radicand is the number or the variables that are inside. Now, first thing you want to do, you want to look for perfect squares. Now remember, I said if this is difficult, if you can't see the perfect squares, you might want to make a factor tree, a prime factor tree, and look for the numbers that double up. Those numbers that pair up, that number hops out and goes outside of the radical. So here I've listed just a couple of the first few perfect squares so you can kind of start recognizing them. So in these I have some variables, but remember, variables are going to act just like numbers. Anything that's to the power of 2, anything that's a perfect square is going to hop out. So that's what we're looking for. We're looking to rewrite things as perfect squares. So 40, if it's not completely obvious, 40 you can break it down into its prime factors. 2 times 20, 20 is 2 times 10, 10 is 2 times 5. Remember, anything that doubles up will hop out, so these guys double up, they're going to hop out. So I'm going to rewrite this. That's 2 times 2, which is 2 squared, right? And then I have this 2 times 5, which is representative of the 10. So I get times 10. Then I have x squared. Now, remember, anything that's written to the power of 2 is going to hop out. So this 2 will hop out, and this x will hop out. So the 2 is going to hop out, and the x is going to hop out. So this is going to reduce to 2x. Whatever doesn't pair up or is to the power of 2 stays inside. So this is 2x times the square root of 10. Alright, looking at 72. 72 might not be obvious, the perfect squares that are hiding in there, but 72 is 2 times 36. Now remember, 36 is a perfect square, right? Now what about a cubed? Well, a cubed is an a times an a times an a. Now remember, anything that pairs up hops out. Well, these guys pair up, right? So an a is going to hop out. So I can rewrite this as 2 times 36, remember 36 is 6 squared, and a squared a. So now everything that's squared will hop out, so this guy will hop out, this guy will hop out. So I'm going to get 6a on the outside. Everything that doesn't pair up stays in the inside, so I get 2a left on the inside. Now, you're going to get really used to doing this process, and you don't have to do this whole process every time you do a problem. You're going to just start to recognize the perfect squares, and you know that when you see this 36, it becomes a 6 when it hops out. You'll know when you see the a cubed, an a is going to hop out because you have a squared there times an a. Alright, so just like we have a product rule, we have a quotient rule that is used whenever we are dividing two radicals. So whenever we have a radical over a fraction, we can break that up into a radical over the numerator and a radical over the denominator. And remember, this goes both ways. This equal sign means I can do either one of these operations. So looking at the square root of 49 over 64, I can break that up into the square root of 49 divided by the square root of 64. Well, the square root of 49 is 7, and the square root of 64 is 8. So 7/8 is my answer now. Now look at over here, square root of 32 over 2. Now, if I were to break this up in the square root of 32 over the square root of 2, I would still have to do some simplifying here because I would have to look for perfect squares inside of 32. Now to make my life easier, you can simplify before you break these up. Well, 32 divided by 2 gives me 16, right? So this actually simplifies whenever I divide 32 into 2, it's square root of 16, which I know is going to be 4, okay? And you would have gotten there if you started doing this way, but it just takes a little longer. So always check if you can simplify first. Maybe you want to do that unless you already have perfect squares. Alright, so adding and subtracting radical expressions is just like adding and subtracting anything that is like terms. So when you think about 4x and 8x, well, they have the same last name of x, right? So normally what we do is we just look at the coefficients 4 and 8, we add those together, and then we tack on the last name of x, so we get 12x. Well, same thing happens here whenever we're adding and subtracting radical expressions. As long as their last names are the same, so as long as they're both square roots and they have the same radicand, a and a, then I can combine the coefficients and I keep the sign there. So looking at this example, I have square root of 3, square root of 3, so those are the same last name. So then I just look at the coefficients, 7 and negative 3. So 7 minus 3, I get 4, so 4 square root of 3. Now looking at my next example here, I have square root of 7 and square root of 7, same last name, right? So that means I just look at the coefficients. Now remember, anything that you can't see is a 1, right? So there's a 1 there. So that's 1 plus 6, which gives me 7. So that's 7 radical 7. Funky looking radical. 7 radical 7. All right. Now over here, these guys don't seem to have the same last name, right? 48 and 75 are not the same. And you can never do this. All right, this is not allowed. Remember, we only combine when we're multiplying, which we're not here. So that means that, maybe, maybe not they could have the same last name, but we have to try. So we have to do a little investigating, and we need to simplify these radicals. So 48 can be broken down into 3 times 16. Well, 16 is a perfect square, right? Its square root is 4. So that means that breaks into 3 times 16 plus, well, the square root of 75. 75 is 3 times 25. So that's 3 times 25, and 25 is a perfect square. So this guy's going to hop out and become a 4. This guy's going to hop out and become a 5. So I'm left with 4 radical 3 plus 5 radical 3. Now look at that. Now we have the same last name, square root of 3, square root of 3. Therefore, I look at the coefficients, 5 and 4, so I get 9 square roots of 3 is my final answer. Now this will not always happen. Sometimes you can't combine them, and that's okay. So simplest form is going to be having them written separately. Alright, one last thing that I want to kind of caution you whenever you're simplifying radicals is to remember the small, simple thing that whenever you have a number in front of the radical, there's multiplication going on, right? So this is 5 times the square root of 49. Well, if I wanted to simplify this, well, the square root of 49 is 7, right? So if I was simplifying this, this would hop out and become a 7. Now what happens now between that 5 and that 7 is multiplication, so this will simplify to give me 35. Okay, this is very simple, but it's often overlooked whenever simplifying. So remember, if you're simplifying, like here I have 8 times the square root of 20. Well, square root of 20 can be broken down to 4 times 5. Remember, 4 is a perfect square, so that guy's going to hop out and become a 2. So that becomes 8 times 2. Okay, so I'm left with 16 square root of 5 as my final simplified answer. So just remember that anything that pops out of the radical multiplies the number that's in front of that radical. Alright, now some of these examples might be a little tough, but I want you to do your best and try them. Remember, whenever we're dealing with variables inside the radicals, anything that can be squared hops out. So remember, y to the 4th, that's y times y times y times y. So anything that pairs up comes out. Well, that pairs up twice, right? So maybe 2 sets of y's will come out, okay? So just remember that whenever you are simplifying. And also remember, I need the same last names over here to subtract or add.